Hey, welcome to High School Physics. My name is Rex. In part 1 of motion, we talked about the types of motion, relative motion, velocity, displacement, distance, and all of that. But in this part, we're going to talk about forces, types of forces, friction, angular velocity and acceleration, and then centripetal force and centrifugal force. First of all, what causes motion? We all know that an object moves from a particular point to another point. What influences the motion of an object? That is force. Force is anything that can change the position of an object or influence its motion. There are two types of forces. There are contact forces, and non-contact forces, or field forces. So what is a contact force? A contact force is the force that has to come in contact with the object before it can influence its motion. An example is the push force, pull force, tension forces. What about field forces? Field forces are those forces that don't really have to come in contact with the object before they can influence its motion. And there are three basic types. There's gravitational force, there's magnetic force, and there's electrical force. There's one special type of contact force that I want us to deal with today, and that is friction. Friction is a contact force that has to deal with the motion of objects. So what is the definition of friction? Friction is a force that opposes the motion of objects. It actually prevents an object from moving. So if let me say this was a surface, all right, because the law of friction is that when an object moves in one direction, friction moves in the opposite direction. So let's say this was a block, and I'm pushing it into the right direction. Friction is acting in the left direction. This follows Newton's third law of motion, which says that for every action, there is an equal and opposite reaction. It means if there's a force acting on an object from one direction, there's an equal and opposite force acting in the other direction. Since one force, which is my force of pushing the object, is acting towards the right, there's an opposite force acting towards the left. It has the same amount of force, but it's just acting in the opposite direction, and that is friction. With several experiments on friction and even its discovery, 5 solid laws has been put up. Number 1, friction acts opposite the force that is acting on the object. So if my force, which is the pull force, is acting in one direction, friction acts in the opposite direction, and it's equal. It opposes the motion of the object. Number 3, friction is independent of surface area. It means that friction only depends on the mass of the object, which means that the heavier the object, the more the friction. The lesser the object or the lighter the object, the less the friction. Friction also depends on gravitational acceleration. It means the more force that is acting upward, which is gravitational acceleration, that we'll talk about later, that is acting on the object, the more friction. The less gravitational acceleration, the less friction. And lastly, the friction also depends on the coefficient of force, which is what I'm going to get to shortly. By the way, if you didn't understand what I meant by friction being independent of surface area and you're confused right now, let me explain it. If I had the surface right here, or let me draw it longer. If I had the surface right here and I had a box, and I'm dragging this box in one direction, friction will always act in this opposite direction. Now suppose I just flip this box down like this. All right, it was no longer an upright rectangle, it was now a flat rectangle, and I started pulling it. The friction would still be the same thing. It's not going to change. So that's what it meant by the surface area. The area of the surface is in contact is not what friction depends on. Whether the area is a large area or a small area, the mass of the object is what friction depends on, not the surface area. So now I was talking about that friction depends on the surfaces in contact. So if I was driving my car on an icy road, the friction would be less. But if I was driving my car on a rough road, the friction would be more. This explains why when you walk on dry ground, you don't fall, because friction is acting on your legs. The force you're using to kick back as you're walking is the same force that friction is using to try and stop your leg from going forward. That is what balances your leg and makes your legs or your foot to walk solidly. But what if there was water on the floor? I'm very sure you might have slipped on water or a banana peel before, and you might have fallen down. Well, you fall because the friction, the layer of water or the banana peel has reduced the friction, thereby making your leg not to have a solid step on the ground. This also explains why they say you shouldn't drive too fast when it's raining, because when it rains, the water on the road has coated the road, and the water now acts as a lubricant or a layer which avoids you and which avoids the tire and friction from coming in contact. That doesn't mean friction isn't there, it just means that friction is pretty much less. And that's why if you want to brake suddenly on a wet road, you're going to start drifting. Lastly, friction also is equivalent to the normal reaction force. That is where I talked about the force of gravity. But the normal reaction force acts upward. The gravitational force acts downward. So let me draw the object so I can draw the number of forces that are acting on the object. So when I draw this surface, complete lines, I have this object which is on the surface and I'm dragging it. So this is force number 1. Let me write that, F1. This is my force, which is me pulling the object. Me pulling the object. Then there's a force acting in the opposite direction based on Newton's third law, which is friction. Friction is F2. But there's also a third force acting upward. That is the normal reaction force. So I will write that F3. Now there's a relationship between friction, I wanted to say fiction. There's a relationship between friction and the normal reaction force. And that relationship is the coefficient of friction. Let me write it down. So friction, you might not understand this now, but we're going to talk about that as we're talking about proportionality in math. So this is the proportionality sign. Friction is proportional to normal reaction force. It means that if the friction increases, the normal reaction force increases. If the friction decreases, then the normal reaction force decreases. So friction is directly proportional to the normal reaction force. All right. So it means that. Let me not write that there. So it means that F, which is friction, is going to be equal to. We have to add a constant. It means that if we're writing an equals to sign from the proportionality sign, as we're removing the proportionality sign and changing it to an equals to sign, we must have a constant. And the constant we use in this case is the coefficient of friction, or mu. This is how it's pronounced. This is a Greek letter, mu. Let me write it again so you can see it clearly. So the constant is mu r. This is the relationship between friction and the normal reaction force. And this constant is called the coefficient of friction. Coefficient of friction. It means that this coefficient of friction depends on the surface. It means the rougher the surface, the more the friction. The smoother the surface, the less the friction. And now that we've discussed about friction, let's discuss about angular velocity and acceleration. First of all, I want you to get a simple picture of circular motion. Circular motion is the same thing as rotational motion, which is basically an object moving in a circular path around an axis. And the axis is the center of the circular path, right? So let me clean this off and explain angular velocity. If you watched my last video when I talked about motion and velocity and displacement, I talked about vector and scalar quantities, which are two main types of quantities. Vector quantities have a magnitude and a direction, while scalar quantities just have a magnitude. So if I said that I walked 5 meters, that is a scalar quantity because it only has a magnitude. But if I said I walked 5 meters to the right, that is a vector because I basically stated the magnitude, which is 5 meters, and the direction, which is to the right. So if I may ask you, because in the last video I said that speed is a scalar quantity because speed is basically dividing distance by the time. If I asked you how fast you were, you would say it's the distance you covered divided by the time. So what is the difference between speed and velocity? Because they're practically the same thing. It's that speed is a scalar quantity because distance is a scalar quantity. Distance only deals with the magnitude of how far you have gone, but it doesn't tell you the direction. But velocity is displacement divided by time, not distance divided by time. So speed is distance divided by time, so speed is a scalar, while velocity is a displacement divided by time. And displacement has a direction, so you must have displaced from one position to another in a specific direction over a certain period of time. So if you're going in a circular path, the speed is constant. What do I mean? The magnitude of how fast you're moving is constant. How fast you're moving over a certain time is constant. But is the velocity constant? Well, the answer is no, because the velocity deals with the magnitude and the direction. If you're moving in one constant direction, okay, your velocity is constant because you have a constant speed and a constant direction. But you're moving in a circular path. So the circular path is constantly changing direction. You're constantly moving in these directions. I'm just drawing tangential lines, and tangential lines are just like surface lines to show the direction of the object. So as you can see, the object is constantly changing direction. So the velocity is not constant, but the speed is constant. The formula for angular velocity is actually written in a Greek letter, and it's this one. It looks like a W, and it's theta divided by the time. It's practically the angle it covers divided by the time. Now there's a relationship between angular velocity and linear velocity, and we're going to find that out now. First of all, just keep in mind that angular velocity is theta divided by time, and keep in mind that linear velocity is the distance divided by the time. Remember that velocity is displacement divided by time, and s is displacement. So s is displacement divided by the time. Alright. Now also keep in mind that theta is equal to the distance divided by the radius. Just keep this in mind. Next, what we're going to do is to make s the subject of the formula. To make s the subject of the formula, I'm just going to bring r over here. So s is going to be equal to r theta. So let me write that again so you can see how I got the formula. Theta is equal to s over r. If we make s the formula, or the subject of the formula, s is going to be equal to r theta. Right? Now, v is equal to s over t. But we know that s is equal to r theta. So v is going to be equal to r theta over t. How will this help us find angular velocity? Well, angular velocity is theta divided by t. If we separate this r from theta divided by t, we're going to have v is equal to r multiplied by theta over t. And remember that angular velocity is the same thing as theta divided by t. So v is going to be r multiplied by angular velocity. This is the relationship between linear velocity, which is v, and angular velocity, which is this letter, this Greek letter. Now we're going to talk about centripetal and centrifugal force. Remember when I told you that whenever there's a force acting in one direction, there's an equal and opposite force acting in the other direction, just like Newton's third law. So here's what I mean. Centripetal force is a force that acts towards the center of the circular motion. Now here's an example. If a car was going round a bend, let me draw a road. If a car was going round a bend, let's say this is the car, alright, there's a force pulling this car towards the center of the circle as the car is orbiting around this axis. Alright, there's this force that keeps pulling the car towards the center of the circle. That is centripetal force. And centripetal force is gotten by the mass of the object, because it depends on the mass. The bigger the mass, the more the centripetal force. So, let me write that down. Centripetal force, or Ft, I'll just call that Ft. Let me clean this diagram over here. And write this Ft in the middle of the board. Ft, which is centripetal force, is proportional to the mass. It means that the bigger the mass, the more the centripetal force. It means that more force is needed to pull the object toward the center of the circle because the mass is increased. Next is the velocity. The more the velocity of the object, the more centripetal force the object would have, or the more centripetal force would be needed to pull the object towards the center of the circle because the speed is more. And lastly is the radius. The centripetal force is not directly proportional to the radius, it's actually inversely proportional. And to be inverse for a quantity to be inversely proportional to another quantity, it means that if a quantity increases, the other quantity that is inversely proportional will decrease, not increase. So it means that the smaller the radius, the more the centripetal force. It means that the smaller the radius of this circle, let's say the smaller the radius, it's going to have a sharper bend. It means that more force is needed to pull the object closer to it. And the bigger the radius, the less the centripetal force would need, because the bend isn't that sharp. So not much centripetal force is needed. So it's inversely proportional to r. If we combine both the mass and the velocity and the radius all together, we're going to get Ft is equal to the mass multiplied by the velocity divided by its radius. This is the formula. Sorry, I drew a line on top of that v. M multiplied by v divided by r. This is the formula for centripetal force. There's also centripetal acceleration, and the formula for centripetal acceleration, which we'll call Fa, is simply the velocity squared of the object divided by the radius. So this is for centripetal acceleration, and this is for centripetal force. But remember, I told you that Newton's third law says that whatever force acts in one direction has an equal and opposite force acting in the opposite direction. Now, the equal and opposite force acting in the other direction of centripetal force is centrifugal force. Centrifugal force is that force, we feel or we attempt to use and counterbalance centripetal force. Let's say your dad is taking a left turn round a bend. Do you suddenly feel yourself being pulled towards the right? Or maybe your mom is taking a right turn towards a bend, and you're feeling pulled towards the left. Or maybe your dad suddenly begins to hit the accelerator very suddenly, and you feel yourself being pulled back. And then maybe your dad suddenly brakes, and you feel yourself being pulled front. This is what Newton calls an opposite or equal reaction force. So when your dad is going around a right turn, he's going around a right turn, and you feel yourself being pulled away from that turn towards the left. That is centrifugal force trying to balance out the centripetal force. That force you feel being pushed towards the left is centrifugal force. And it's kind of irresistible. It kind of happens it happens exactly every time you take a turn around a bend, except you want to stop it, which actually really isn't possible. And lastly, I want to talk about torque. Have you ever been riding your bike around a bend and you can't possibly turn your bike around a bend without having to take a bend? And you have to actually lean towards the bend you're going. If you're going towards the right, you have to lean towards the right. If you're going towards the left, you have to lean towards the left. Why is this? This is because it is not possible for a bike to take a left turn straight. But the bike has to lean towards the bend. The bike has to balance out the centripetal force that is acting on it. But your body wants to keep moving straight. That is inertia, one of Newton's definitions. And your body wants to keep moving straight, but the bike wants to turn. If you keep putting yourself straight and your bike is bending to turn, you will topple over because your body is moving straight, but the bike is turning. As the bike is turning, you have to lean forward to balance out that centripetal force with the bicycle instead of following the inertia. Lastly, at the beginning of this lesson, I forgot to tell you that there are two types of frictional forces. There's the static or limiting friction, and then there's the dynamic or kinetic friction. Static or limiting friction is that friction you have to overcome for an object to begin to move. It means that if I had an object on this table, there's a certain amount of force I would need to overcome friction for me to be able to push this block across the table. That is static or limiting friction. And then there is dynamic or kinetic friction, which is the friction that you have to overcome for an object to keep moving. Remember when I told you that friction keeps on increasing as your force increases? Yes, this is true. So if you keep using that same force, there's a certain force you have to overcome for an object to keep moving. And if you don't overcome that force, your object will come to a stop. That is what they call dynamic or kinetic friction. It's time for the questions. Give me 2 advantages and 2 disadvantages of friction. If you enjoyed this video, please like, subscribe, and share with at least 3 people who you know don't have access to basic education or who is bold enough to explore homeschool, and I'll see you in the next class.